This is an image of Earth during its icebound period. At this moment, Earth's average temperature drops to a chilling -50 degrees Celsius. Apart from a small amount of liquid water at the ocean floor, every other place on the planet is covered entirely by ice and snow. This isn't a scene from a science fiction movie. It's a real event that happened in Earth's history. We call this the Snowball Earth era. It was the coldest period in Earth's history, where everything from the poles to the equator was frozen solid. How did life survive in such an extreme environment? Today, let's travel through time and space to explore why Earth became a snowball world and what caused the planet to thaw out. Around 700 to 600 million years ago, Earth went through two incredibly long and severe freezing events, known as the Sturtian and Marinoan ice ages. During these periods, the ice sheets rapidly expanded towards lower latitudes, even reaching the equator. The entire globe was frozen, turning Earth into a giant snowball. If you looked at Earth from space, you would see it wrapped in layers of ice, several kilometers thick, looking like a frozen hell. In the tropics, which should have been hot and teeming with life, it turned into an endless white wasteland. Massive glaciers appeared everywhere, and the entire world was ruled by cold. There was no flowing water in the rivers, no rain fell from the sky, and the average temperature dropped to a chilling -50 degrees Celsius. At the poles, temperatures were even worse, reaching as low as -130 degrees Celsius. In this lifeless world, the only sounds were the cracks in the ice and the winds blowing across the frozen surface. It's estimated that nearly half of the world's oceans were frozen at the time, and the entire Earth was trapped in the grip of glaciers. Luckily, at this time, Earth had not yet evolved humans or other land-based life forms, so extinction was not a threat, though it could have been. So, how long did Earth stay frozen, and how did it thaw out of this icy prison? The story begins about 800 million years ago. At that time, there was a supercontinent called Rodinia, which was centered around the equator and contained most of Earth's land. The land was mostly barren desert, with slightly higher areas covered by ice and snow. Life was still very simple, consisting mainly of microscopic organisms living in the oceans, enjoying a relatively mild marine climate. But that didn't last long. Rodinia began to break apart along the equator, like a giant puzzle being shattered. This rupture had significant consequences, changing the rainfall patterns of the oceans, increasing the flow of rivers and rainfall, and accelerating erosion. This had a huge impact on the carbonate cycle, because rainwater dissolved carbon dioxide from the atmosphere, forming carbonic acid, which chemically reacted with surface rocks, dissolving silicates in the rocks. These dissolved substances were carried by rivers into the oceans, where they eventually precipitated as carbonates. This process removed large amounts of CO2 from the atmosphere, reducing greenhouse gases and causing Earth to cool. Polar ice caps began to form slowly, and the ice itself altered rainfall patterns, reducing rock erosion and further decreasing CO2 removal from the atmosphere. At this point, Earth completely lost control and temperatures plummeted, a trend that couldn't be stopped. Earth began to fall into a vicious cycle because cold temperatures lead to more ice formation, and ice reflects sunlight back into space, causing polar ice caps to advance toward the equator. This process took only a few centuries to 1,000 years, and Earth's average temperature dropped by 50 degrees Celsius, freezing the planet completely for 58 million years. So, how did Earth begin to thaw? You might think of the sun, but at that time, the sun was still young and not nearly as strong as it is now. To thaw Earth, the sun would need to be at least twice as bright as it is today, which is clearly unrealistic. The real savior was Earth's own hot inner core. Only by Earth's own efforts could the temperature rise. Although much of Earth's surface was frozen, tectonic plate movements and volcanic activity continued. Volcanoes sporadically erupted, releasing heat and large amounts of CO2 from the Earth's interior into the atmosphere. Over the course of 58 million years, these greenhouse gases accumulated in the atmosphere, their concentration rising steadily. Eventually, it reached a critical point, and when the CO2 level was 350 times higher than it is today, the super-strong greenhouse effect took hold. These CO2 molecules acted like a thick blanket for Earth, absorbing much of the sun's radiation. Earth began to warm gradually. Starting at the equator, the ice began to melt, and dark-colored land and oceans reappeared, absorbing more solar energy and further driving up the temperature. This process was like a domino effect. Once it started, it couldn't be stopped. In just a few thousand years, vast bodies of water and land re-emerged. Earth was released from its frozen grip, beginning a massive thawing operation. However, this thawing brought about a super-hot period. Temperatures soared to extreme levels. Liquid water at the equator reached nearly 50 degrees Celsius, and the atmosphere was filled with water vapor. This caused frequent storms and hurricanes, as if Earth had entered a chaotic, steamy era. This scorching climate lasted nearly 1,000,000 years, until continental rocks had absorbed enough CO2 to bring Earth's average temperature back to more reasonable levels. As Earth thawed, rapidly reproducing microorganisms and algae quickly filled ecological niches, creating conditions for more complex life forms to emerge. These microorganisms not only provided rich organic matter for marine ecosystems through photosynthesis, but also helped regulate CO2 levels in the atmosphere. Geological activity also played a crucial role in the restoration of ecosystems. Minerals brought by volcanic eruptions enriched the soil, promoting the growth of vegetation. The appearance of this vegetation further improved soil structure, providing a habitat for more life forms. During this process, biodiversity rapidly increased, and new forms of life began to appear. Everything on Earth started moving in a better direction. So, will Earth always remain in this warm state? Will the next ice age ever come? If another ice age does arrive, how will life on Earth evolve at that time? Today, modern scientists are studying ice cores, ocean sediments, and other sources to analyze long-term trends in Earth's climate. These studies show that Earth's climate system is a complex, dynamic system. It is not static, but is influenced by multiple factors, including solar activity, changes in Earth's orbit, atmospheric composition, and human activities. At present, human activities are of particular concern, as increased greenhouse gas emissions are altering Earth's climate patterns. This may delay or even prevent the arrival of the next ice age. However, this human-driven climate change could also bring about new challenges, such as more extreme weather events, rising sea levels, and a gradual loss of biodiversity. Therefore, understanding Earth's climatic history not only helps us predict future climate changes, but also equips us to better tackle current environmental issues. In short, Earth's climate system has undergone numerous shifts, from ice ages to warm periods. Each change has had a profound impact on life's survival, biodiversity, and even evolutionary paths. But no matter how Earth changes in the vast expanse of the universe, it remains but a tiny speck among countless celestial bodies.